chapters, we've been working with one sample, but let's say that we want to compare something. Like we want to know, do girls study more than boys? Do we want to know if drug A works better than drug B? If we want to compare two populations, population 1 and population 2, and we want to use proportions, then we need to use two sample procedures. So that's chapter 10. So if you recall from chapter 7 and in your formula sheet, you know that sampling distributions of a sample proportion have the properties right here that first of all, in order to do inference, you need to have that your population is nearly normal. And you also, in order to do your calculations with the standard error or the sample or standard deviation of the sampling distribution, you need to know that it's independent. And then, of course, the center, we expect that center to be centered at the population center. So if we're trying to do a comparison of two populations, you can look on your formula sheet, and there are formulas for comparing two populations. So that's what we're working on today. So here we have sampling distribution, and we have two populations, and we have looking at that homework completion, comparing, well, North Country and Lake Region. At school 1, 70% of their students did their homework last night. So we would say population 1 is 0.7. Notice how I'm using a subscript to show my groups, in population 2 is 0.5. So if we have counselors at school 1 and they take a simple random sample of 100 students and they record the sample proportion, that's going to be a statistic for that school. And at school 2, they could do a simple random sample of 200 students, and they could record a sample proportion of kids who did their homework, and that would be a statistic. Notice the hats on the statistics. That would be for their school 2. And then what could we say about the difference of these sample statistics? Well, if we use our Fathom software, which generates first of all the approximate sampling distribution of the p-hat for proportion 1, we expect it to be centered at p sub 1. So that's why this graph is centered at p sub 1 equals 0.7. So it's centered there. And group 2, they're going to be centered at their population value of 0.5. But then the difference is going to be, so the difference for P1 minus P2, notice that on your formula sheet, you'll see that there are those hats on there to have a proper notation. And so then we can take the difference, and we expect this to be centered at 0.2, and there it is centered at 0.2. So that's, and then we can see that the standard deviation of the sampling distribution, they're right there, and then we're going to find out how to calculate this value right here. We're going to find out. Okay, down below. So yeah, and that value right there, you can see that from chapter 6, when we have two independent random variables, x and y, we can find the standard deviation through the variance. And so if you think about this number right here, what's one way that we could have gotten this is to go through the standard deviation values for the first group and then the second group. There's our variances. So we're going to add it up, and that's going to give us our variance for the difference. And then if I take the square root of this, let's take the square root of this. So that means that my difference will be 0.058 if you do that. And probably I should have, instead of using X and Y, probably would have been better to write my notation to look like this, because really I'm working with populations, and I've defined them as P sub 1 and P sub 2 for this situation. So this shows the normal curve for our sampling distribution, centered at centered here at the bottom at the mean value, which is going to be your P sub 1 minus your P sub 2. Notice, although this is a sampling distribution for the statistics, it's the population values that help you figure out what the actual expected center of it. So if we're going to be doing inference, we always have to check our conditions. And so our conditions, and these conditions need to be true for both groups. So we're going to need both groups to be random. And so we're going to have to check both. And remember, violations of randomness doesn't necessarily mean that you're unable to do inference. It just means that you have to think about what population you're really getting answers for, if you're even getting answers for a population, or maybe it's just the group that you studied. Then we're going to need to know the shape. So that's checking if it's nearly normal. If somebody tells you that n times p and n times q, so we would need that for, they need to be greater than or equal to 10, and it needs to be true for both group number 1, but also group number 2 needs to be meeting this as well. So you're going to need both groups. And then we're going to need independence. So let's see, where's the independent? Oh, right here, independence at the bottom. And so that would be for both groups, either the 10% condition, where n is less than or equal to, let's see, n is less than or equal to 10% of n. Let's write that again. And then that goes for group 1. And that goes for group 2. If you have a finite population, or maybe it's independent because it's not a finite population. Now, in all of these checks up here, there was no hat. So when you're checking your conditions, you are trying to use the population values. However, especially in the situation where you're doing an interval, you might not have a statistic. So you might not have, the population value. You might not have P1 or P2. When this happens, then you will check using the statistics. So if you don't have parameters, these are parameters. When this happens, use p hat as your best guesses, your best estimates. So we are going to be doing intervals today. We are going to be doing tests today. Right here, there's a very important case. This is the case when you think there is no difference between the two populations. Like if I say that there's no difference between boys and girls studying habits, then, or between school 1 and school 2 studying habits, then I am going to, for my test, I will need to pool the test, and we're going to do that. Your calculator can do that automatically when it does a test. But for the interval, do not pool the interval. Okay, so we're gonna do those two cases. So that is when you think that this mu for the P1 minus the P2, when you think that value P1 minus P2, when you think these were the same, so if these are the same, that difference would be 0. When you think that that difference is 0, that's when you pool. Only for the test. Only for the test. So we will do it. And so more about the pooled samples. So that again, that's when you think P1 is equal to P2. So when you think P1 minus P2 is equal to 0, when the two parameters are the same, then we're going to think of these guys as really being the same. So we're going to put them together. We're going to take in the sample in your SRS, the people who are studying, for example, doing their homework, and the people from the other school who are doing their homework. We're going to put them together, and we're going to take the total population from group 1 and the total population from group 2, and we're going to put them together because we think that they really were all the same, so why not put them all together and find one proportion, one pooled proportion to represent everybody. And so that, and why do we do that? Why do we only do this for tests? It's because if you think about your test, if you think about your hypothesis, the hypothesis was about the population. And if you just said that this population, that there is no difference, right? If that's what we're starting off, we're assuming this null is true, although we would never state that we thought it was true. Since that is our null condition, our null hypothesis, and we're saying that we think they're the same, then like, why are we treating them as different groups? Let's just put them together, call them one group, because we think the boys and the girls, or school 1 and school 2, we think they're all the same. So like, we're going to put them together. And then we're looking for enough evidence. We're looking for enough evidence to say they're not the same. That's if our p-value is low enough, if our p-value is less than the alpha that we've specified, then we have the evidence for the alternative hypothesis. We have the evidence that's going to make our conclusion state that we think that really we have to reject that null. So again, just for tests, and we think it's difference when it's this situation where we think there's no difference, then we're going to combine and compute our z statistic. Okay, and it's proportions. So proportions, just like in the last chapter, chapters 8 and 9, we saw that for proportions, that's going to be z statistics. So we're using that curve. And I personally like to use this format for my pooled standard deviation of the sampling distribution for the difference of the two proportions. I personally like that, but if you look on your formula sheet, they have written it like on the formula sheet, it is written like, find that on your formula sheet. They have that pooled statistic, and they've written it as a standard error, which a lot of times I'll write SE, but yeah, I'm just trying to copy what's done this sheet right here. Okay, let's see here. So they're going to take, well, for the, that's what they've written down here. That's a pooled value, that P sub C. And then they go like this, 1 over n sub 1 plus 1 over n sub 2. And so what that's done is they've just factored out the pooled proportion. But personally, I like this version up here better, because I feel like it's really the same setup as what we were doing, but it works every time, but it's just like, okay, I put the pooled value in both places where I would have put P sub 1 and where I would have put P sub 2. But as you can see that on the formula sheet, they do have on there this version right here, they do have this formula, so you can remember how you get that P sub C, that pooled proportion. You can see how you got that. So that's on the formula sheet. Now we'll go to the next page and let's do an example. All right, well, got to do all the conditions for this thing. We got to define what we're doing. And okay, so we are looking at 2 large high schools. That's good information to know that they're large, each with more than 2,000 students. In a town, we've got school 1, so maybe we'll write out some of the information that we've got here. We know school 1 is 0.70. We know at school 2, we've got 0.50. The counselor at school 1 takes a simple random sample of 100 students, so we know we have got 100 students. They did not tell us what this was. They didn't tell us what the value they got was. But at school 2, they took a simple random sample of 200 students, and they didn't tell us what that was. But they did tell us that P1, P hat for school 1, the statistic for school 2, they got 0.1. And so we know that P sub 1 minus P sub 2 will be the difference of homework completion proportions at the 2 schools. Make sure you define what you're working with. Really important in difference of proportions to say which one you do first, because it's not going to matter which one you do first. The only difference is like whether or not you'll be testing the left or the right if you're doing a one-tailed test. And your test statistic might be on the other side of your mean, but it's not going to change your p-value. Your result will be exactly the same. So, okay, we got to check the conditions for inference. It was an SRS at school 1 and at school 2. So that was given. So that's good. That meets that condition. Okay, now we got to check if we're independent. This is so that we can do our calculations of our standard deviation for the sampling distribution if it's independent. So 100 students, because this is a finite population, so we do need to use a 10% condition. That means that we would need to have over 1,000 students there. And then there were 200 students at school 2. Oops, let me put a little 1 on there because that's school 1. And let's check school 2. 10%, sorry. So we would, and then since each school has over 2,000, this is good. We are independent, and then we want to check for nearly normal. Now, if we had the p-hats, we would not check them because we have the p. Remember, this check is with n times p. It's going to be without the hat if we can. So I'm going to check that, and n times q for this is school 1. So 100 kids, it's 70. Oh, well, yeah, I probably should have just checked this other side. This is going to be the one that controls this situation. 30 kids, so that's good. Whoops, I forgot to write. So that's good. School 1's good. Oh, this is going to be the same check for both of these 100. Okay, and then I'll just write it out, though. Feel free to fast forward through this brief moment. Okay, so that's meeting the conditions for inference, Matt. So let's write that. Conditions for inference are met. So make sure you say what you're going to do. And let's see, this is asking us to do a interval. Okay, they're asking us to do an interval. So we will do a 2-sample Z interval for difference of proportions. And we're going to do this at an alpha of 0.05 because they did not specify in there what level to use. So we're going to use a 95% confidence level for this situation. Now, do we pool? No pooling. Why? Because it's an interval. So no pooling on an interval. So let's go up, and because I've got some room up here, and I'm going to start writing out my interval. So just like before, we've got our statistic plus or minus our critical Z times our standard error for the difference of our two proportions. So this right here, we need to use the statistics. We have to use the statistics on this because intervals are using the data to give you a window of what you think might be true. So if I'm using statistics, I'm going to be using, here we go. I'm going to be using that. That's going to be this. And then I'm going to be adding and subtracting my critical Z, which I know for a 0.05 divided by 2, that's 95% confidence level. I know that's 1.960. So that's something that I've got memorized. And then here I'm going to have my standard error for that difference of my two proportions. Okay, so this value they gave me, this value I'm going to have to calculate. And so let's calculate that value so we'll have that. Again, this is using, I would like to use I would like P sub 1, P hat. I would like that one, and I would like these values. I would like to use these right here, but I don't have them. So the best guess I have at them is going to be P sub 1 and P sub 2. Now I wish I could use the sample values. Those counselors, they didn't tell me the numbers, for goodness sakes. Just can't get good help nowadays. And so I've got to use my other values, and I'm going to put those in there, and I get 0.057879, just keeping it long to like, so like that's what this right here, this is what I think this is. It's that right there. Okay, so now let's go down, make myself a little room here and like actually calculate this interval. So I know what this is right here. I know what we think that is. So we think that is 0.10. So let's do our 0.10 plus or minus our 1.960 and bring that standard error down. So 0.057879. And so I get, and remember this symbol in the middle here needs to be parameters. And what is this parameter? What's it going to be? It's going to be P1 minus P sub 2. Okay, so we think, now if you had done the P sub 2 minus the P sub 1, then this number would have been positive and it would have been on the right. And this number 0.213 would have been negative and it would have been on the left, but it wouldn't really have changed anything. It would just be, that's why it's important to know which direction you're working in. So I'm going to write my conclusion. So with 95% confidence, the interval from negative 0.01, whoops, 3, I'm going to write that a little nicer. Negative 0.0134 to 213 captures. I like the word captures because it implies that you hope that you got it. Captures a difference in the proportions of homework completion at the two schools and then I just want to mention that, just to mention, like, so this is a result that they just had. This is our window based on our statistic, the best that we could. Oh yes, more COVID-19 information. Okay, but so this is what we expect, but just remember, I guess I'll write this in green. Remember, we thought, or we believe P sub 1 minus P sub 2. We believe, and this is, based on the parameter, we believe it's going to be 0.7 minus 0.5. So we believe that it's 0.2. So now when I look at their report, when I look at this right here, where would 0.2 fall? It would fall within this window. So since 0.2 falls in the window, the interval of 0, 1, 3, 4, 2, 0.213, we would not question the validity of their report. I mean, it looks like their data would not question the validity of their report. We basically, it looks like their data is supporting what we kind of thought of all along. Report, and don't think the school has changed. You know, as part of, for now, that's what we think. Okay, so that was the interval. Now we do a test. So now we're doing the test. We're gonna say that the conditions are met because it would be exactly the same. You know, because we did that all on the other page. So like, I mean, how much can we really do? And in fact, we actually on the other page had found the standard deviation of the sampling distribution because we didn't have values for the statistics. We actually used population values. So we actually had found this on the other page as well. So I'm gonna write that number down that we had on the last page. And so now we're going to have to do a two sample Z test for the difference of two populations. Now, let's say that we look at that and our initial thought about these two populations was that that's what we think is really true about the populations. That is not 0. So do not pool on this test. Do not pool this test because it is not a piece of 1 minus piece of 2 equals 0 situation. So we're not going to pool. So let's continue up here. So that's good because that means we can use this value that we had found. So we're going to write our hypotheses. Okay, piece of 1 minus piece of 2 is equal to 0. Sometimes some people like to write it like this, you know. That's totally acceptable as well. Oh, but we don't think it's 0. We think it's 0.2. So actually that would have been a pooled situation. This situation, we kind of do have to write it the way I am. Piece of 1 minus piece of 2. And did they want to know if the schools one was lower, higher, what? They didn't say. So we're just thinking that it's not 0.2. So that's a two-tailed situation. And so here's our middle. Remember, the middle is always the population value, which in this situation is going to be this right here. So that's, here I'll even write it with the symbol. That's right off the formula sheet if you want to get your symbols right. So we've got that, and we're going to be looking for evidence, and we're going to have to double that value when we get it, and that it will be what we're checking. So okay, so we're checking that, and so we are going to be doing our Z. And so if you think about your Z, it's that statistic minus the parameter. So statistic minus the parameter over your standard deviation of the sampling distribution. So over that standard deviation of the sampling distribution. So what's your statistic? Your statistic is your P1 minus your P2 with the hats. So they said that they went out there and they got 0.1. They didn't tell you what the individual values were. They just told you that they got a 0.1. So we're going to put that 0.1 right here. And then we know what we think the truth is, and we are going to put that right there. So there's those values. And then we just found this value on the denominator. Well, I'm going to erase that just so I can write it in there. And we think that that number is 0.057879. And just to remind you, that was this right here. Right there. So like we've got that, and so that's going to give us our test statistic, which if we punch that in correctly, we get negative 1.7277. So that's this number right here. So right there. And so then that is the value that we're going to then find our p-value. So we're going to find the probability that a z will go below a negative 1.7277. And that probability is 0.0426 dot, 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 dot. I've got on my calculator, but it's two-tailed, so I need to multiply it by 2. I've got to double it for that two-tailed situation, and I get, okay, so failing to reject, which is the same conclusion that we got with the interval, that we had no evidence to doubt the validity of the report, or we didn't have no evidence. We have some evidence, but not enough evidence. Not enough evidence to doubt it, and that's the situation here. We have not enough evidence, so since the p-value of 0.085 is greater than alpha equal 0.05, we fail to reject the null hypothesis. And there is not significant evidence that the difference in the proportions of homework completion let me just move this up, are different at the two, or are different from 0.2. Oops, let me say at the two schools. Different from 0.2. Okay, so there you go. Even though they got a 0.1, that's not statistically different enough from 0.2 for us to reject that. So yeah, I guess those guys might have done good work. Good. So then we're going to move on to another situation. So that was a test, and that was a test that did not need to be pooled. And so now I'm just going to do some more examples, and then on page 7, so I'm going to do another example, but then on page 7 we'll do a pooled situation. So as part of the Pew Internet and American Life Project, researchers conducted 2 surveys in late 2009. The first survey asked a random sample of 800 U.S. teens about their use of social media and the internet. And the second survey posed similar questions to a random sample of 2,253 U.S. adults. And what they saw. 73% of the teens and 47% of the adults said they use social networking sites. So let's use these results to construct and interpret a 95% confidence interval for the difference between the proportion of all US teens and adults who use social networking sites. So, got our conditions. And I guess I'll write them all out because I know you can fast forward through this portion. The main thing is you may just want to check that since we don't have parameter values, we're going to be using our statistics as our best guess, and so we will use the p-hat values as needed. Okay, so you can fast forward, but I'll write it all out since I know you can fast forward. Okay, so is it random? It was given. It was a SRS of teens and adults. Was it independent? Finite population requires a 10% check, so is 800 less than or equal to 10% of N? There are more than 8,000 teens. And for the adults, 2253 less than or equal to 10% of N, and there are more than 22530 adults, so that works. You may want to add to here maybe a T for teen as a subscript, and here an A for adult for a subscript, just to distinguish those ends from each other. And now, like nearly normal. And so we've got N times P, and then equal to 10 for the teens. And then, so we've got, let's see here. Well, of course, this side's going to meet, but I'll just do it anyway. And then 0.27 times 800, and that has to be greater than or equal to 10. That one's definitely meeting. I mean, of course, this one would meet because it, okay, and then let's check for the adults. For the adults, greater than or equal to 10. Of course, we're going to have this meeting too. Okay, so, and they said their percentage was 0.47 times 2253. That's going to be a big number. And this is the one that's going to control anyway. And I get 1058.91 is greater than or equal to 10. So that's definitely, just in case you wanted to know what the other number was. Let's see, this would be 0.53, 2253, greater than or equal to 10. So I get 114.09. Yeah, so anyway, that's, conditions for inference are met. And so let's, really important to define what you're going to do. I like that the fact that this number is higher than this number. So I think you're better off for your difference to specify that you're going to have the teens be first. So I'm going to say proportion of teens minus the proportion of adults will be the difference of teen proportions of teens and adults using social networking. Okay, so that really important to distinguish what order you're going to be doing them in. So I am going to take my value that now intervals are based on, I should say what I'm doing. Never said what I was doing. I am doing a 2-sample Z interval for difference of proportions. And so I need the statistic. I'm going to need the statistic right in here. And that statistic will be what I get from my stats. And so I got 0.73 minus 0.47. So that is 0.26. So I'm going to just put that number right here. This is Z. We're finding Z right now. And we are going to subtract the, oh wait, what am I doing? Erase that. I'm trying to do an interval. I'd start the video over, but I don't know how to do that. So anyway, so we're going to take our statistic. Oh, we need our critical Z. That's what we need. And we're going to do this at, they didn't say, so let's just go with our usual 1.960. So our interval will be 0.26 plus or minus that critical Z value of 1.960. And now I need to put my standard error into this spot, which I, of course, never calculated. So there's a lot to do in these things, isn't there? Okay, so let's see here. We got to not pool because we're doing an interval. Never pool on an interval. This formula is right on the formula sheet. I'm using my hats, my statistic values, because an interval is supposed to be based on a statistic. So putting those values in. All right, now, so now I'd complete, this is, 0.26 plus my margin of error. That's my margin of error. And then 0.26 minus my margin of error. Those two things together make the margin of error, the critical Z and the standard error. And, oh, great, I didn't actually punch this into the calculator. All right, it's good stuff. Gotta punch it in. 297, and then in the middle it's going to be what I notice that I don't have hats on there, and then I just got to go back and subtract it. Subtracting my margin of error, and so I get 0.22, and then it was 296, so I'm gonna call that 3. Okay, so there's that, and then I can, write my conclusion. All right, so with 95% confidence, the interval from 0.223 to 0.297 captures the true difference in the portions of teens and adults using social networking sites. And so if somebody asks me, oh, do you think the two groups are the same? I would say, are they the same? Well, if they were the same, you would have expected there to be no difference. And so then you would be looking for the value of 0. If they were both the same, you'd expect them to be 0. And when I look at that value, 0 is not in the interval. So if you were asking me, I'd say there's a difference between teens and adults in their use of social networking. So what if we were interested in doing a test and the same situation of teens and adults, and we're doing a test, and we really think that the true difference is 0.2. So what we're saying is we think the proportion of teens minus the proportion of adults, we really think, whatever the numbers are, we're thinking it's 0.2. And so I could write my hypotheses for this situation, and I would say that I think that this value is 0.2. And then my alternative, though, and do I want it to be greater, less than? And if they don't specify, then you're just looking for, is it different from 0.2? And so we would want to find the standard deviation of the statistic. Now, we would want, when we're finding this right here, standard deviation of the statistic, we would want to use our population values. So we would like, whoops, that's supposed to be a 1. Erase that. Got to keep, my writing's messy enough, but we would want to use this, but we don't have them. We don't have those values. So only the, actually teens, and the adults, only those are available. So in this situation, we're going to have to use that same number that we had before. So we're going to use as our best estimate of our teens minus our adult proportions. Our best estimate is going to be the number from the other page, with the calculation being on the other page. That's our best estimate of that number. That's the only thing that's available for us. So we're going to do that. So, and then we're going to find the Z statistic for this. And so right here in this spot would be our, this would be what our stats told us. So that's going to be our teens minus our adults. That's going to go in there. And we saw on the other page that was 0.26. And then we're going to subtract here. This is going to be the population value, which you can always find right here on your null hypothesis. That number is going to go right here. So that's that number. And then we wish we had population values, but we don't. So we're going to just use our standard error, but that's our best guess at that. And so I get 3.176. Looks like a lot of evidence there. And so then you could get your p-value. Whoops. P-value. And that would be the probability that a z goes above a 3.176, and then don't forget that you need to double it to get the answer. So like that's definitely going to be evidence that, because that's going to be a pretty low p-value at a z-score of that high. You're going to have something pretty high. So you're going to have the same conclusion as you did with your interval, that you would not think that that you wouldn't say that they were really 0.2. That's going to be a lot of evidence. But like, let's say that you really thought the groups were not different at all. If you really thought that the proportion of teens minus the proportion of adults was 0, this is where we must pool for a test. You have to pool the test. You don't have to pool an interval, but you do have to pool the test. So we would have our null hypothesis. Oh, these are teens minus adults. Our alternative hypothesis. Telling me that I've got a pool. So I've got that standard deviation of the statistic that I used before is not going to work, because I need to pool. I need to find my new pooled proportion. There were 584 people, and for teens there was 1,059 for adults out of, and then see how I'm putting the two groups together. Like if you're telling me there's no difference between these two groups, then why didn't you just take those 584 people and then just say, well, they're really the same as the ones who are adults who are doing this. So there's really 1,643 people who are on social networking, and there's 3,053 people in all. And so like really the proportion of people, because they're really all the same, 0.53859. So like that's my P. So then I've got to get my pooled value, which probably should have given myself more room. But so I'm going to get my standard error that's pooled. And I'm going to then, I like to just write the same numbers. But see, as you put this into here, you have to separate the groups out for the work here. I'm going to run out of room, I think. There's 800 of these, and then I'm going to add that to, this is 6184, sorry, and there's 2253 of these guys, so it's going to find that comes out to be 0.020518. Use lots of decimals if you're not going to have rounding errors. And so then that puts into, yeah, and if you use the formula sheet version, you'd get the exact same number. And so then I can go in, I got to find the test statistic. And so my Z, okay, again, it's 0.26 was the difference that I saw of the two things. Now I've got to, and I've got to put my minus my parameter. Remember, you think that they're the same, so it's 0, so that's going in as 0 from that null hypothesis. Look at your null hypothesis. That'll tell you what number goes there. Okay, and then I get my Z of 12.67. Holy mother of something. That is a lot. That is really, really high. So our p-value, if you told me that a z going greater than a 12.67, and then of course, well, I'm even going to find out what that is roughly. Okay, 4.5 times 10 to the negative 3 times 2, because you got to double it for the two tail. 8 point, well, let's call that 9 because my rounding. Wait, oh, negative 37. Sorry, that was to the negative 37. Times 10 to the negative 37. I mean, holy cow, that is, basically zero. Basically not possible. So that's a tremendous amount of evidence that teens are different from adults in terms of their use of social networking. So now just to try to do this with a calculator and to get comfortable with the calculator and how the calculator will know how to pool on a test, I just want to look at these two schools and the children who came to the schools without eating breakfast at two low-income elementary schools. And so we have, from our sample statistics, we have that there were 19 out of the 80 students at school 1, and the sample statistic at school 2 says 26 out of 150 did not eat breakfast that morning when they came to school. And in order to, before we use our calculator, knowing that the conditions have been checked, I just need to decide what my hypotheses are, because that will be really important for if I am going to be pooling or not pooling. So I have my hypotheses that they are looking at, does this data have convincing evidence that there's a difference in the population proportions? They're thinking that school 1 and school 2 are the same, and they are wondering if they are different, and so no, not equal to 0. If I was doing a check of greater than or less than, it might be nice to know what the proportions were, because maybe I would have liked to have changed the order in which I wrote those to have the positive side of the curve. So this is going to be a 2 sample z-test for proportions. And it's important to know that it's for proportions, because that'll help me find the information in the calculator. And because of this, we know that it needs to be pooled. So we will need to have a pooled proportion of the 19 are put together with the other 26 who did not eat. And as if the schools were one school, 80 and 150 go together. That gives me a proportion of 0.195652. So now I'm going to use the calculator, which I now know how to do on this situation. So if I go to my calculator and I click on Stat Tests and scroll down to the 2 proportion z-test, not the 2 sample, that's for means, but the 2 proportion, where I've already entered in my 19 out of 80, my 26 out of 150. And if I do the two-tailed test, I'm going to calculate. And you can see that the output actually even has the pooled values. So it starts with my z-test statistic, my p-value, which is the probability of being both sides, because it was a two-tailed test, so it would have been around 0.12 for the one-tailed. And then I've got my school 1 sample statistic, my school 2 sample statistic, but notice that the pooled p-value is 0.195. That's exactly what I got as well. So we can get all this information from our calculator. I'll just write these things down on this paper, that we were able to get our z-test statistic, and that was using the standard, the pooled standard deviation of the sampling distribution, and that was 0.168. It gave us our p-value, and it was two-tailed. That number was, let's see, 0.2428. It gave us that. It gave us the pooled statistic because it did pool it for the test, and so there was not statistical evidence to conclude that these schools were different from each other. Because I'm doing a two-tailed test, I could, if I wanted to, just to check what the calculator can do for an interval, I would be doing a 2 proportion z interval, and that would be not pooled. If you are doing an interval, you do not pool because it's not based on everybody being the same. It's based on each group individually. So if I went to my calculator and I go to the tests and I go to an interval, which is below the proportions. Let's see, 2 sample, that's going to be for means. 1 proportion. 2 proportion z interval. There's my numbers, and my confidence level is 95%, which fits that 0.05 level. Confidence intervals are two-tailed. And so notice that they don't report a pooled value because confidence intervals are never pooled. So don't pool on your confidence interval, but there's my confidence interval, and it's important to know what was first and what was second in order to know how you would write your p sub 1 minus your p sub 2 with no hats in the middle of your confidence interval. So one more study, and this one is a study of cholesterol. They're wondering if this cholesterol, this drug that reduces cholesterol, if it's going to help men who not have heart attacks. So they had volunteer subjects. They were assigned random treatments, so they are going to be able to make some conclusions. They have the men who took the drug that's supposed to reduce their cholesterol, and they had a control group of 2,030 men who took a placebo. During the next 5 years, they had 56 men had heart attacks in the drug group and 84 in the placebo group. So we're wondering if this is statistically significant. So I would set up in my placebo group, and I had 56 out of 2051, and I have 84 out of 2030, and I am wondering if my I want to know if my if there's going to be if it's going to lower my heart attacks. So let's see, we'll go PG minus PP. No hats on these. So the equal sign at the null hypothesis, and I'm wondering if it'll lower it. So if I think about my curve, I want the PG to be lower. So if in the middle I have 0, if I want my PG to be lower than my PP, I should be looking at this side. This would be PG minus PP and it being lower. So if I want to reduce my situation, and because I'm saying no difference, I need to pool. And so let's see what the calculator says about that. Okay, so I've got my 56. Okay, 56. 2051. 84. 2030. And then I needed to look at my P1 being lower than my P2. And that number comes out. There's my Z test statistic, my p-value of that happening, my P1, my P2, and it's been pooled because I was doing a test of no difference. And then, of course, you could do an interval for that if you wanted, and you would not pool on an interval.